All right, good afternoon, class. So today we're actually going to start diving into Chapter 5. So what are we doing in Chapter 5? So mostly with Chapter 5, we're going to be cleaning up a few concepts that we haven't covered yet before we jump to what are called antiderivatives, or you may have heard them called integrals. Uh, Integrals, integration, antiderivatives, all that good stuff. We're actually going to see in chapter 6. So for chapter 5, this is where we get our introduction to exponential functions and logarithmic functions. You've likely seen these kind of functions before, maybe just off the top of your head. Me saying those words doesn't ring any bells. That's fine. I'm going to introduce them today as if you've never seen them before. We'll talk about what they are, what are their applications, in particular in banking, and what kind of example problems you can solve with them. And then as we continue in Chapter 5, we'll start to cover how to take the derivative of such functions. So up to this point, we've talked about how to take the derivative for any polynomial, any fraction, things such as that. After this chapter, you'll be able to add to that toolbox derivatives for exponential functions and logarithmic functions. After this chapter, you'll be able to take the derivative of anything you could possibly want. The only thing that we are not covering in this class is trigonometry. That's simply because it's not a prerequisite, or not a prerequisite, it's not a requirement for calculus with non-math science majors. So for the purposes of this class, it's not required, so we're not going to go over that. Just save some time for you guys, save some headache. And there we have it. So let's go and get started in 5.1 today, where we have an introduction to exponential functions. So let's talk about it. So we are in 5.1, section 5.1, and we're talking about exponential functions. What is an exponential function? Exponential function. This is any function that's of the form f of x is equal to some constant c times some constant b. Now this b is specifically a positive number, and also not equal to 1, because if it equals 1, then it doesn't really do anything here. But this b is raised to the r times x power, where r is some other constant. So in this case, up to this point, we've seen equations where we have x raised to some constant power, but for exponential functions, we flip it on its head and we say, what if we have a constant raised to the x power? So it's called an exponential function because the x variable is in the exponent now instead of being the base. All right, so that's the basic format for an exponential function. C and R are constants. B is a positive constant. And B does not equal 1. Because if it did equal 1, well then 1 to any power is just 1. And then the equation would just be a constant function equal to C, which that isn't very interesting. We've already talked about constant functions, so that doesn't really bring anything new. So we're assuming that b, in this sense, is not equal to 1, but it's some positive number. So that's an exponential function. And we say that this is an exponential function with base b. So b for base, anytime you see these exponential functions, these powers where the x is in the exponent, whatever is down here is called the base. So this is an exponential function with base b. Okay, so let's keep moving forward. What are some general facts about these functions? What do they look like? Well, in general, if you have the function, let's say, f of x equals 2 times 2 to the x. What does this look like? Well, with these functions, you can always find your y-intercept very easily, because if you plug in x equals 0, then we have 2 to the 0 is 1, and we have 2. So we have a y-intercept at 2. And so this is actually a fact that's true of all exponential functions. The y-intercept is at 0, c. Because if you zero out this guy, then you're left with this c for your y value. The one exception you want to be careful of here with this rule I have written, this is assuming you just have x with some coefficient. However, if you have cb raised to the x plus 1, well, in that case, if I plug in 0, then 0 plus 1 is 1, b to the first is b. The intercept in this case would be at 0 cb. So this rule here, with the y-intercept being 0c, only works when you have x times a constant and you don't have any plus or minuses. If you have plus or minuses, like in this example, then this is not going to, then your y-intercept is going to be something else and it won't be the c. So be careful of that. All right, what else do we know about exponential functions? Well, the x value is in the power up here. And I'm just going to go ahead and draw you what this graph looks like. Something like this. So the first thing to note is our domain, you can plug in any x. So what's our domain? Well, that's from negative infinity to infinity. No vertical asymptotes. What else do we know? We also know that in this case, so long as b is some positive number, which is what we assume here, it's a positive constant, then, and I want to be careful about how I say this, because it's not always true. Yeah, the textbook had a typo here, and I wanted to skip over the typo. So scratch that, forget what I was saying there. The domain is negative infinity to infinity. That's good. Now we also want to note that the x-axis is a horizontal asymptote. And this is true for every exponential function. Asymptote. Why is that? Well, think about it. Where can this function equal 0? In other words, 2 to what power equals 0? Well, 2 to any power is going to result in some number that's not 0. Even if I plug in 0 up here for x, 2 to the 0 is 1. So there's no exponential x that I can plug in here that's going to make this equation equal to 0. So my function can never equal 0, and so we have a horizontal asymptote there. So that's also a nifty little thing to take note of. Let's see, what else do we got? We can also see that the function is continuous. Now, why is that helpful? Well, that's just helpful because it tells us that the limit exists at every given point. So for any x on this line, you can find where the limit is going to there, and you're going to be able to find the limit. It's defined, which is nice. So you know the limit is always going to exist at any given point on this function. Okay, cool. Now what? So that covers the basic principles of what an exponential function is, but now we'd like to look at its application. In particular, you're going to see these equations pop up over and over again in banking type questions. Questions where you're trying to calculate interest. Maybe you want to know how long it's going to take for your deposit to double if you just leave it in the bank. So on and so forth. All of these kind of questions are related to exponential functions. So let's talk about it. Interest. So when I write these equations, let me first describe what some of these variables mean. P is going to stand for invested principal, which just means how much money did you deposit in the bank at the very start of this question. At the very start, how much did you deposit? And that's the amount that's going to be increasing based off of interest. So that's principal, P. Next, we have R, and this is lowercase r. Here, R stands for annual interest rate. Annual interest rate. And more specifically, we want it written as a decimal. Why? Well, oftentimes in these questions, it'll say maybe you have an annual interest rate of 6.3%. Okay, that's all fine and good, but what does 6.3% mean in terms of an equation? Well, a percentage, when you think of it this way, this is 6.3% out of 100%, right? I mean, that's what a percentage is. We have up to 100% that we can have, and it's 6.3 out of 100%. So, well, this fraction, and if you put this in your calculator, you'll see it as well, this fraction is actually equal to 0.063. And there you have it. So you can, anytime you have a percentage, divide it by 100 and you'll find out what the decimal format is. But if you want to save yourself the trouble of having to divide it every time, just take note of the fact that whenever you want to change a percentage to a decimal, all you have to do is move the decimal place twice to the left, and that'll tell you what the number is supposed to be. And that's going to be true for every percentage. Given any percentage, maybe you're told that it increases at 0.1%, which is more realistic for what banks actually do. Then this as a decimal would be, if I move it twice, 0.001. And there you have it. It's that easy to change a percentage to a decimal. You are going to need to know how to do that for these questions, so make sure this kind of thing makes sense to you and you know how to do it quickly and correctly. All right, so R is for annual interest rate. It is the amount of interest that you gain each year. Okay, so that's useful. What else do we have? Next, we also have N. This is lowercase n. Here, N stands for the number of times per year. The number of times per year interest is compounded. And this comes into play really because depending on your bank and depending on the question, sometimes a bank might say, oh, we compound interest quarterly, or oh, we do it monthly, meaning every month you gain some interest, or quarterly, which would be 12 divided by 4, that's every 3 months, or that's 4 times a year that it gets compounded. Whatever it may be, this N is how many times a year interest gets added to it. That could be monthly, so that's 12 times. It could be quarterly, so that's 4 times. It could be daily, in which case that's 365 times. So on and so forth. N is an important number here you want to keep track of. And then lastly, T is the number of years you want to calculate for. So what is my my account balance after 5 years, after 6 years, after 3.5 years? How much money do I have in my account based off of all of these other variables we have here? And so now that we have all this together, we can now look at the first equation. This equation is called interest compounded n times, so n, that's the same n up here, n times a year. This is a very important equation you're going to be using over and over again with these kind of questions. So the equation is A stands for account balance, so your balance is equal to P, however much you started with, times 1 plus R, what's your interest rate, divided by the number of times it's compounded, raised to the n times t power. And so PR and N are all going to be constant numbers that you know that you're going to plug into this. And so when you plug the numbers in, this is going to be an equation with a number times a number raised to the t power. In other words, this equation is an exponential function. So this is why we're talking about exponential functions now. So this equation, very useful, very important. We're going to see some examples here in a moment with how you're actually going to solve these problems. But for now, just write down the equation, and then we'll talk about it in a moment. There's also going to be one more equation we're going to need for this section for 5.1. Now this other equation also requires that we know about another number. So this number we need to know about is the number E. What is E? Well, if you have a calculator or you can actually Google it, either way you can find this number. E is approximately equal to 2.718, and then so on and so forth. This number continues on forever. It continues on infinitely, the same way that pi does. Pi goes on forever, so does E. So this is a number that you do not want to estimate as 2.7 or 2.71 or 2.718. Anytime you're using a calculation with E, you want to make sure you're using a calculator or you're using something online. Whatever it is you're using, you want to make sure you're actually typing in E, because that's going to give you more accuracy than if you just put in 2.7. But more specifically, what is E? How do we get this number? It's a little beyond the scope of this class, but we also know that E is defined as the limit as x goes to negative infinity for 1 plus 1 over x raised to the x power. Now, why is that true? Again, that's a little beyond the scope of this class. If you want to try to prove it to yourself, you can type into your calculator increasing numbers of x. Now it's increasing towards negative infinity, so you want to plug in bigger and bigger negative numbers. So you plug in bigger and bigger negative numbers into this little formula, 1 plus 1 over x, all raised to the x power. They're going to find the bigger the number you plug in, the closer it's going to get to this 2.718 number. So a little more than you needed to know, but point being, there's this number E that we're going to need for this next equation. So this next formula is for interest compounded continuously. So instead of doing it n times a year, they are continually adding interest to your bank account. So this isn't something that banks often do. It is something that can sometimes happen for special cases or some kind of special accounts. So it's not super common, but it is something that can happen. So in this case, when interest is compounded continuously, we have a different equation for A. Here, A is equal to P, that's our same principal, times E, that's our number E over here, raised to the RT power. And there you have it. So you can clearly see that there are some differences between these two equations. You are going to need both of them for different questions, and that's just going to come down to make sure you read the word problems very carefully, because it will specify if they're asking for interest compounded some number of times a year, or they'll say interest compounded continuously. You want to make sure you keep track of the distinction between the two, because you will solve those two questions differently, and these two equations will give you different answers. So make sure you keep track of that. Right, so there we go. That covers the basics for the equations we need to solve these exponential functions relating to some banking applications. So let's go ahead and take a look at a few examples, and then we'll move on to section 5.2. So let's see, I think I'll leave that up what we have to the right. And I'm also going to recopy our equations up above. So we have A is equal to PE to the RT power. That's for compounded continuously. And then we have A is equal to P times 1 plus R divided by N raised to the NT. Yeah, and this is for compounded in n number of times. So there we go. These are the two equations we're going to use. Let's see, do those show up? Yeah, I think y'all can read them. Let me know if this marker doesn't work for you guys and I won't use it in the future, but I think that's clear enough to see on the screen. All right, so let's keep going. So oftentimes these kind of questions are going to be presented in word problems the same way that we've seen a lot of our other business application questions. So you want to make sure you pay attention to the wording. And of course, for the sake of simplicity, I'm just going to read it to you and highlight what we need to know. So here we go. The question says, Mary has recently inherited $9,000. So she just got $9,000 from somewhere. That's pretty nice. Which she wants to deposit into a CD account. So she wants to deposit this into an account where it's going to gain interest. In other words, if this is her initial deposit, this is P. Okay, let's keep going then. She has determined that her two best bets are an account that can compound annually. So she's got two accounts she's comparing. Account 1, I'll abbreviate that as ACC1. Account 1 is an account that compounds annually. Compounds annually. So how often does it compound? Once a year. So here, n equals 1. It compounds annually at a rate of 4%. So R equals 4%, or in other words, that's 0.04 as a decimal. Okay, so we got our N, we got our R, we got our P, and so we can go ahead and make our equation here. So account 1, A1, is equal to 9,000 times 1 plus 0.04, and it's compounded annually, so n equals 1. It happens once a year. So 0.04 divided by 1 is just 0.04. And to the nt, so this is just to the t power. So there's our account 1. Now next the question says, and in another account, account 2, that compounds daily at an annual rate. So this is a daily compoundment. So how many times a year does it compound? If it happens daily, that's 365 times. So it's compounded daily at a rate of 5%. So go ahead and change that to a decimal. That's 0.05. So again, we have our N, we have our R. So we can write that A2, account 2, is equal to 9,000 times 1 plus 0.05 divided by 365 raised to the 365t. Okay, so there we go. We have our two equations that represent how much is going to be in the bank account after t number of years, depending on if the money is in account 1 or account 2. Okay, so let's keep going. So now the question says, which account will pay more interest and how much will the balance be in that account after 3 years? So we're looking at which one is going to pay out more over 3 years. Which one is going to give Mary more interest? So all we got to do is plug in 3, or t equals 3. So a1 of 3 is going to equal 9,000 times 1.04 raised to the third, which I'd worked out ahead of time, is 10,123 and 78 cents. Okay, so not bad. That's the account balance after 3 years if it's put in account 1. And now we look at account 2 when t equals 3. Then here we're going to have 9,001 plus 0.05 divided by 365 raised to the 365 times 3 power. And again, I worked out it ahead. That's 10,456 and 40 cents. Now for these problems, I'm rounding to 2 decimal places because in terms of money, going beyond 1 penny doesn't make much sense, so we just round to the second decimal place since that's where the pennies are. And there we go. So we can see from these two numbers that account 2 will accrue more interest over the course of 3 years, and so Mary should go with account 2. And there you have it. So that's the final answer for this question. And really, if we were looking at the question before we tried to solve it, you might have been able to tell just by looking at these numbers that account 2 is going to be better, because not only was it compounding more times than account 1, 365 is much bigger than 1. Not only is it compounding more often, but it's compounding with a higher interest rate. 5% is bigger than 4%. So this account 2 is pretty much better in every way possible. And there you go. That's an example question you might have to deal with in 5.1. So there are some other examples, but I want to make sure we get through 5.2 before I finish this lecture. So let's go ahead and switch gears to 5.2, and then we may come back to some other example questions later. So let me move these magnets here. All right, and here we go. So now we are moving into 5.2. So what is 5.2 all about? Well, we've talked about exponential functions, but now we're ready to talk about logarithmic functions. In particular, we care about natural logarithms. So what's a natural logarithm? Natural logarithm. So a natural logarithm is of the form f of x is equal to c times the natural log of x raised to some power r. Now this r in here, this is on the x, where c and r are just constants. And this ln I have abbreviated here, that's the abbreviation for natural log. So when you see equations that have ln here, then that's your logarithm. So what are some other things to note? This has the interesting property that if EY is equal to X, if this is true, which is where my if and only if comes. If and only if just means that if this, then the next statement is also true. but the next statement also implies this original statement. So if e to the y equals x, then y equals the natural log of x. So this is pretty nifty here. This also gives us a few other nice rules. Whenever you have, so the natural log, it's oftentimes not written, but it's implied that natural log is base e of x, and we're saying this is equal to y. So the natural log is base e, and what this is telling us is that when we have y equals the natural log of x, and we have this implied base e, then we have the nifty trick that whatever the base is, in this case it's e raised to the power of what this equals also equals what's on the inside of our natural log, x. That's what this rule is telling us. So anytime you're dealing with natural logs, this is a nice little trick that allows you to flip the base around and get rid of the natural log and just play with the variables by themselves. But you can also go backwards. You can change this back into this format. So either way is good. This is also useful because if we're dealing with other logarithms that are not base e, for example, the traditional logarithm is base 10, which in one way to think about, what is a logarithm, and you know what? I've misplaced my calculator. Give me 1 second. All right, I'm back. So what I wanted to point out here was log base 10, which is the traditional log, if you look at a calculator or whatever, is really asking how many times, 10 to what power is this guy on the inside? In other words, how many times does 10 multiply into x? And so if we have the question log base 10 of 100, which you can type into a calculator, you're going to get an answer of 2. That means 10 to the second power is equal to 100. It's how many times does 10 multiply into 100. But the nifty trick with this is that the same rule we have up here also applies here. You take your base, raise it to this power, so 10 squared, and then that's supposed to equal what's on the inside, 100. And obviously, 10 squared equals 100. So, point being, if you have log base 10 of x, this is also saying if this is equal to some y, then we're asking 10 to the y is equal to x, which is the same relationship we have up here with this logarithm, natural logarithm. So this is a very important little rule that you're going to be able to use when you're trying to simplify logarithms, when you're trying to simplify natural logs. You're going to use this over and over again. This works for any log base system. So if it's log base b containing a, and this is equal to c, then using the same rule, this is b to the c is equal to a. And there you have it. And my purple marker is dying on me, unfortunately. So there you go. This is a very important rule. And so we have noted here that this works for natural logs, but in more general terms, it works for any logarithm with any base. So, nifty trick, keep that in mind. All right, so what else? What else do we know about natural logarithms? Well, we also have that the domain, oops, that is the wrong pen. The domain is 0 to infinity. So this is non-inclusive. We can't plug in 0, but we can plug in any number bigger than 0. Why is that? Well, if you graph this function, then you're going to see it looks something like this. Whereas we get closer and closer to 0 from the right side, this function is disappearing to negative infinity. But for the negative numbers, we don't have anything. You can't plug in a negative number into a logarithm. So keep that in mind when we're thinking about logarithms. If you've got a negative on the inside, then you've maybe messed up somewhere. So you might want to backtrack on what you're doing. So the domain for this function is 0 to infinity. And then lastly, I would just like to highlight some logarithm rules that are very useful for trying to simplify logarithms. So what are these rules? Well, these are probably rules you've seen before, but in case you haven't, then I'm going to go ahead and put them up here so that you'll know what to expect. So first things first, and if we're assuming m and n are positive constants, then our first rule is the natural log of m times n. So if you have the natural log of something times something, then you can always pull it apart into the natural log of the first guy plus the natural log of the second guy. But we can keep going and suppose that you have m divided by n. Then in this case, it's the natural log of m minus the natural log of n. And so you can again break it apart when you have a division or a multiplication on the inside. Also, we have that if we have the natural log of m to some power r, then that power, as long as it's on the inside of this natural log, can always be pulled outside as a coefficient of this natural log. That's going to be useful when you have things to powers, and then you can pull the powers to the outside. You may be able to cancel them with some other fractions that you have in the equation, so on and so forth. This is going to be a nifty trick. You want to make sure you hold on to that. Furthermore, if the natural log of m is equal to the natural log of n, then this implies that m equals n. So if you have two natural logs that equal each other, then their insides must be the same thing. M must equal n. And this is also true vice versa. That's why I've got this drawn with arrows going both directions. If you have m equals n, then you could choose to take the natural log of both sides of the equal sign, and then you still have this statement that's equivalent over here. So this is also nifty. If you're trying to solve for some x, but then maybe in the algebra you end up coming down to a natural log equal to a natural log, you can further break it down by just looking at what's on the inside. But you want to make sure that 1, your natural logs have the same base, and 2, you want to make sure they have the same coefficients. In this case, they both have a coefficient of 1, and they both have a base of e. So that's important to double check that before you just assume they're equal. And then some other little nifty tricks. And this you can get from the calculator, but it's worth remembering just to save yourself some time. The natural log of 1 is 0. The natural log of e is 1. If you have e raised to the natural log of x power, then the e in this natural log are going to cancel each other and just leave you with x. But more specifically, in more general terms, if you have some base b raised to some log that has the same base, then the b in those logs can cancel and you'll be left with x. That's why when you have e to the natural log, which the natural log has an implied base e, that they're able to cancel each other. So you want to make sure you keep track of both of these. That's a useful trick. And then lastly, we have the natural log of e to the x. Now we've already discussed that this power we can move out to the outside, so that's just equal to x natural log of e. But natural log of e is just 1 like we have down here, so this is just x. So anytime you have the natural log of e to the x, it's just x, and you can save yourself the time of trying to figure out what it is. So these are all good rules to remember for how you can simplify natural logarithms, but these same rules also apply to any logarithm with any base b. So these are useful. keep them in mind, and you're going to want to use them in section 5.2 when it'll ask you to simplify these guys. Okay, so now for examples. So for our first example, we're going to go back to another banking question, except in this case, it's going to force us to use natural logs in order to solve. How is that going to happen? Well, you'll see as we get there. So here the question says, and let me flip to the correct page. So, if $6,000 is invested, what the heck? If $6,000 is invested, in other words, $6,000 are deposited, this is our principal. It's the amount of money we're starting with. If $6,000 is invested at 7.5% compounded monthly, So they just gave us a lot of information here. One, we know our rate is 7.5%, or in other words, 0.075. We also know that n, if it's compounded monthly, that's happening once a month. There's 12 months in a year, so this is happening 12 times a year. So we can make our equation before we even know what they're asking us, we can go ahead and make our equation here. So A is equal to 6,000, 1 plus R divided by N, all raised to the NT. And there we have it. There's our equation for interest that is compounded monthly. So what we'd like to do next is, well, actually go ahead and read the rest of the question. So if $6,000 is invested at 7.5% compounded monthly, how long will it take for the balance to double? In other words, we want to know when will our initial investment double. We want to know when will we have $12,000 in our bank account. And now that we have this set up, this is now just an algebra equation where we want to solve for t. So let's go ahead and do that. The easiest thing to do is go ahead and get rid of our coefficients, and then we'll be able to take the natural log of both sides and pull the power down, but you'll see that as we come to it. So I'm going to divide by 6,000. So 12,000 divided by 6,000 is going to give me 2, and so 2 is equal to 1 plus 0.075 divided by 12 raised to the 12t power. And now if I take the natural log of both sides, I've got the natural log of 2 is equal to, and when I take the natural log of this guy, this is where our rule comes in. If I have the natural log of something raised to a power, then I can pull the power down outside as a coefficient. So 12t comes down outside as a coefficient, and so I'll have 12t times the natural log of 1 plus 0. Oops. That's a bad 0. Let me try that again. So we have the natural log of 1 plus 0.075 divided by 12. So some things to note here. The natural log of 2, if you put that in the calculator, is really just some number. And the same here, the natural log of 1 plus 0.075 divided by 12, that's just some number. So even though it doesn't look pretty, if I want to solve for t, all I have to do is divide 12 and this natural log over. So I'm going to have the natural log of 2 divided by 12 times the natural log of 1 plus 0.075 divided by 12. And that's it. We now know what t equals. Now, of course, it's like, hey, but I don't know what that number is. That doesn't make much sense to me. If you then type that into a calculator, then you're going to get 9.27. So in other words, for this person who's investing $6,000 into this account, it's going to take a little over 9 years before he's going to double his investment. So it's going to take some time, but once he gets there, it'll be nice. Let's see. I think, yeah, that about covers all I wanted for 5.1 and 5.2. The only other type of questions you might see for this section could be that maybe they'll throw an equation at you and they'll just ask you to simplify what the natural log is using these rules that we've outlined here today. So that's just an application of what we've already done, so no big deal there. Of course, if you have any questions, concerns, don't hesitate to email me and we can talk about it. Otherwise, we also have our Q&A coming in later in the day, so of course, bring your questions to that and we'll talk about any concerns you have then. Otherwise, that's all I have for you. So, with that being said, I wish you the best of luck.